Okay, let's finish this guy up. Now, when we talk about VSEPR theory, we're talking about valence shell electron pair repulsion. This is allowing us to determine 3D shape around an atom. Lewis structures do not tell us three-dimensional shape. With the rules that we had earlier in chapter 7, it just allows you to see how atoms are going to be connected. Are there going to be single, double, triple bonds? Are there going to be lone pairs? Are there going to be resonance structures? But they tend to be flat, and not all molecules are flat. So we're going to skip over hybridization for a second, and we're going to talk about shapes here. All right, valence shell electron pair repulsion. Now, what do you know about electrons? They're negative. What do you know about negative charges? They repel each other. So bonds are made out of electrons, and bonds repel each other, and lone pairs repel each other. So they are going to spread out around an atom to minimize that repulsion, right? And that gives us very predictable shapes. That's where this comes in. You guys hopefully are working on memorizing these geometries. We're going to start off with the smallest ones. We're going to start off with 2 sets of electron groups and 3 sets of electron groups. Now, I've split this up into bonded atoms versus lone pairs. Now, that is always about the central atom. You're not looking at every lone pair in the molecule. You're looking at lone pairs on a central atom. VSEPR theory is only referring to geometry around one central atom. So I've drawn both beryllium beryllium dichloride and CO2. You can practice drawing those. In a previous video, we went through the rules there. Beryllium is a exception to the octet. It's perfectly fine with just 4 electrons. Carbon is not, so we had to share electrons and we got double bonds. But both of these have 2 bonded atoms and no lone pairs. So it doesn't matter that they're not identical. They both have 2 bonded atoms and no lone pairs. When that happens, those 2 electron groups, the bonds, are going to spread out as much as possible, which is going to give you a linear geometry, right? They're going to get 180 degrees apart. You do need to know that bond angle. Moving on, and that's really all you can do. If you remove one of those atoms, you just have a line. That's not going to be a question. So we're going to move on to 3 electron groups. Now you are going to either be dealing with 3 bonds, no lone pairs, or 2 bonds and 1 lone pair. Either way, it's going to add up to 3. The electron geometry is based on how many electron groups, lone pairs or bonds. So whether we are talking about CO3, 2-, the carbonate ion, or sulfur dioxide, you have 3 electron groups. So you are going to get those groups spreading out to give you 120 degree bond angles. All right, it's going to get as far apart as possible. It's called trigonal planar. You're going to notice that anytime the lone pair number is 0, the electron geometry and the molecular geometry are the same. So that is what you see here with carbonate. 3 bonds or 3 bonded atoms, no lone pairs. So 3 areas of electron density, spreading out 120 degrees. Now, when you get to, and we'll come back to that slide. Let's go to the molecular geometry page. Here we go. Once we look at sulfur dioxide, it's 3 sets of electrons all repelling each other. So it makes sense that it has trigonal planar electron geometry. But oftentimes when we talk about shape, we're talking about what shape do the atoms make. So if we're thinking about what shape do the atoms make, the sulfur and the 2 oxygens are just a bent shape with that 120 degree bond angle. It's a little bit smaller than 120, but it's about 120. Lone pairs wind up being a little stronger than bonds. So what you have to know is that if there's 2 bonds and 1 lone pair, it's going to be trigonal planar if you look at all the electrons, but it's going to be bent if you're asked about the shape. When we move on to our 4 sets of electron groups, right, we're looking at 4 and 0, 3 and 1, or 2 and 2. Now, when we think about the tetrahedral geometry, right, that's where it really starts to be more noticeable that Lewis structures, right, they don't show you three-dimensional shape. Methane here, CH4, is not going to have 90-degree bond angles. It's easier to draw it that way, though, because drawing in 3 dimensions can be tough. So we have 4 bonds, no lone pairs. They're going to spread out as much as possible, and you're going to get 109.5-degree bond angles. This is a tetrahedral molecule, right? No lone pairs, so that's also the shape of it's the electron geometry and the molecular geometry. Now, if we start removing bonded atoms and replacing with lone pairs, then, of course, the shape is going to change. So here, with ammonia, you've got 3 bonds, 1 lone pair, so it's still 4 areas. So you're still going to get that tetrahedral shape, or that tetrahedral electron geometry, I'm sorry. But if we think about the shape in terms of just the atoms, we get this little pyramid, right? So we're no longer looking at a lone pair up there. You get this little triangular pyramid. And so that is known as trigonal pyramidal. I think we do have a better picture if I scroll over of the trigonal pyramid right here. Now, if we have 2 bonds and 2 lone pairs, you should be pretty familiar with this little guy, water. Water is not linear. There are 2 lone pairs that are going to repel these 2 bonds, and so you're still going to get tetrahedral electron geometry. But again, if we just focus on the shape, we have another bent molecule. Very similar to sulfur dioxide, but with a smaller bond angle. It's more closely related to tetrahedral, right? Around 109.5, whereas this guy was 120. You're going to continue on for the trigonal bipyramidal if you have 5 groups, an octahedral if you have 6. But for those, you're not responsible for the bond angles. They get to be a little bit more complex, meaning that there's more than one. So for instance, trigonal bipyramidal, when you have 5 groups, you wind up with 90 and 120. So you have like a trigonal planar in the middle and then like a little top and bottom. It's a trigonal pyramid, but then there's another one on the bottom. With octahedral, you have 90 and 180 degrees, but I'm not expecting you to know those. I do expect you to know these shapes, though, these molecular geometries. If you have 5 bonds and no lone pairs, then electron and molecular are the same. They're trigonal bipyramidal. If you've got 1 lone pair, notice they did number of electron groups here, whereas I did bonded atoms, so they're all 5 here. So this table's a little bit different than what you have in your notes. But if you have 1 lone pair and 4 atoms, it's going to be a seesaw. 3 atoms and 2 lone pairs, you get the T shape. 2 atoms and 3 lone pairs, we've got another linear molecule. Once you go to 6, you have, and I've got pictures over here, let's see, of sulfur hexafluoride and xenon tetrafluoride. They both have 6 groups. If you have 6 atoms and no lone pairs attached to the central atom, it's going to be octahedral. You'll still have octahedral geometry for the electrons in the xenon tetrafluoride, but now you have 4 bonded atoms and 2 lone pairs. So when you have the 2 lone pairs, that's going to give you square planar geometry. You have to do practice with this. I've got an extra practice set up on eCampus in your practice folder, and you've got some in homework. And next week's lab gives you a lot of extra practice, right? So that's experiment 9, Lewis structures. You're going to have to do that anyway. So if you're looking for more practice, start on your lab. The last little topic that we want to talk about is hybridization. Now, this goes in valence bond theory, but I think it's easier to kind of give you a shortcut here at the end if you already know VSEPR theory. So let's talk about hybridization. We'll go back, sync these notes up. Okay. Now, we talked about the bond angles up here, right? These are going to be 109.5 on methane. It's going to take on a tetrahedral shape. We know this. One, it's going to be the lowest energy to put those bonds far apart. And two, because now we have been able to study the structure, measure the bond angles. Initially, though, this doesn't make sense, right? Carbon, let's make it so I can write. Carbon has a full 1s, a full 2s, and 2 electrons in 2p. Now, if we saw bonding like we did with O2 or N2 on the last page, we would expect to get maybe 1 sigma and 1 pi bond, but we don't. We get 4 equal sigma bonds here. So what's happening? To form the 4 bonds so that we can get a full octet, the orbitals of an atom hybridize. They change. The orbitals of a molecule are different than orbitals of an atom that's not bonded to anything. You've got to remember what an orbital is. An orbital is simply the mathematical description of where the electrons can be found. And when 2 atoms form a bond, where those electrons can be found changes. So what we see here with something like methane is we need the 2s and the 2p orbitals to combine. So it's like, I think of it like Play-Doh. I roll them all together, and then I split them back up into 4 equal balls. So 4 equal orbitals called now the sp3, because it's made from an s and 3 p's, orbitals. They're all equal size, they're all equal energy, and they spread out to give tetrahedral geometry. Okay, so we had to have an S and 3 P's, right? So that's 4 hybrid orbitals. You are going to need hybrids for every lone pair and sigma bond. So we're going to keep that in mind down here under shortcut. Lone pairs plus sigma bonds. That's how many hybrids we need. Okay? Now, when we think about something like, right, methane, it has its 4 bonds. That's also going to apply to something like ammonia. Anything with tetrahedral geometry is going to electron geometry, mind you, is going to wind up with sp3 hybridization. Notice that was there for tetrahedral, trigonal pyramidal, and bent, all of the tetrahedral electron geometries. It's to give those bond angles. All right, what about sp2? So I'm going to take a look at something like the carbonate, right? So we drew it above, but it's something like this, right? You have 3 bonds, 3 sigma bonds, 1 pi bond, no lone pairs. All right, that's why down here we just say sigma bonds. So we need 3 equal energy orbitals. We need 1 p orbital to do the pi bond and the double bond. So what we're going to see for sp2, let's draw this over here, is we have our full 2s, we have our half full 2p, and we're going to just take 2 of the p orbitals this time. And we're going to mix those together, and we're going to get 3 sp2 orbitals because they were made from 1s and 2 p's. That's going to leave 1 of the p orbitals unchanged. So you're going to have 3 equal energy orbitals to make your sigma bonds over here. And you're going to have 1 p orbital to take care of the pi bond and the double bond. Anytime you have 3 sigma bonds or a combination of sigma and lone pairs that adds up to 3, it's going to be sp2 hybridized. Sp hybridization. when we saw the carbon dioxide. You have 180 degree bond angles. You're going to take the, the 2s, and this time, only one of the p orbitals. You're going to mash them up together, roll them back out. You're going to get two equal energy SPs. There we go. Two equal energy p orbitals. And so you're going to get your sigma. That's going to be from the SP. Let's change this color for a second. And then you're going to have the pi and the pi. And that's going to come from those p orbitals. All right, now, if that all just made you super sad, don't worry. Can you count? Lone pairs and sigma bonds, that's how many hybrid orbitals you need. However many hybrid orbitals you need, that's how many letters you need, right? I needed 4 for methane up here. So 1, 2, 3, 4, an S and 3 Ps, that adds up to 4. Here I had 3 sigma bonds with the carbonate, S and 2 Ps, that adds up to 3, sp2 hybridized. Same down here with this carbon in the carbon dioxide. You need 2 hybrid orbitals, so the S and the P. Now, we can do this on larger molecules as well. That's why I've drawn the sulfur hexafluoride over here. Let's count, shall we? We have 1, 2, 3, 4, 5, 6 sigma bonds, no lone pairs. So I need the S. There's only 3 p orbitals. That only adds up to 4. So where do I go next? I go to D. I need 2 more, so I'm going to take 2 d orbitals. So S, all 3 p's, and 2 d's. Notice you see that up here. Xenon tetrafluoride is octahedral electron geometry, but it's a square planar molecule. But it's the same principle if I'm talking about hybridization. 1, 2, 3, 4 sigma bonds, 5 and 6 when we add in the lone pairs. So it is also going to be sp3d2. It's just a matter of counting. So again, if the explanation of why we think about hybridizing, right, hybridization was developed to explain the actual bond angles we saw. But if you can count, you're well on your way. Make sure to practice this